Hi, sir.
So we will start discussing the task that has been given to you. So Akshay will walk you through the concepts, and after that, he will also tell you about the how the code is working and what you need to do ahead. So please be ready with copy and a notebook and a pen so that you may note down the important points. Okay.
Yeah, yeah, better.
Thank you so much, Vedant. So we'll proceed with the discussion. Today's discussion is about quantum walk, so forward and reverse approach specifically, and this is quite a little bit different from the conventional quantum walks. So, this is an inspired approach, and what exactly we mean by quantum walks here, will explain you in the context of the project. So, without any further ado, let me share my screen. Okay, so is my screen visible? Hello?
Yes, yes, yes.
Okay, yeah. So, yeah, just a sec. Okay, okay, okay. So, yeah. Um, today's topic of discussion is quantum forward and reverse approach. I'll explain you in a simple language and what in detail of what this project means, and uh, so for classification approach basically. The classification. Yeah, excuse my handwriting still. Yeah. Anyways, so moving ahead. Um, yeah. So there will be an add option here, right? Okay. Okay. There is answer this. Okay, fine. Um, so um, uh, Before going to details of what exactly this is, so have you attended the first session? Like Prashant and so have you guys attended the first session?
Yeah, yeah, Akshay, good.
Yeah. So in the first session, so I'll explain you in brief what exactly is a quantum algorithm, what I mean by quantum inspired ML. Basically, in quantum computing. So what exactly is a quantum computing? We have our input qubit state. This is nothing but you will have your input qubit state in 00 format. This is in cat notation, bracket notation, and then you will apply a quantum circuit. That quantum circuit will map this input vectors, this ground states of the qubits, to a state that will be your input vectors. So that will be our quantum encoded classical data set, right? This will be your quantum encoded classical data set. Okay, so we have studied 6 types of encoding for it, 6 types of quantum encodings. Now you have to map this into your target vectors for classification approach, which we have already studied using a quantum circuit here. So what exactly this quantum circuit is nothing but in Heisenberg matrix formalism, it's some unitary matrix under unitary constraints. So what exactly are the unitary constraints? You might be aware about, like it's u into u dagger is equal to I, and then the note or the document share with you, like it has the details of what exactly the unitary matrix is. So basically this unitary can be decomposed into U3 and a C0 gates. So these forms are quantum circuit basically. So U3 will have 3 parameterizations of 3 quantum angles, and C0 will have 2 parameterizations of control and target qubits. So this forms are basis of quantum computing, and this if we like run it for specific classification, specific application, let's say classification, it forms the quantum algorithm for that specific classification application. So what exactly happens here? As basically we know that this is nothing but a matrix. As in, if we consider, so we must be aware about linear algebra. What exactly is a matrix vector multiplication? So matrix vector multiplication, what it is, it's happening here. As in, this unitary matrix is getting multiplied to your input vector. But now like since we are in inspired domain, like we don't need to do this, so we are starting a circuit from here itself. As in, we are taking the input vectors, we are applying our unitary of segregations, which can be found by 5-6 method, like you must be aware if you attended the first session, which is ML, then SVD, then QR, unitary encoding, etc. Other QNN, and then AAB and other algorithms are also there specifically for finding quantum circuit. But this is the circuit we'll be considering, because we don't need to map, because we already have our quantum encoded vectors here. So we don't need to map it onto the quantum computer for it to know, because we are processing it on a classical processor itself. Okay, so what exactly this does is basically it applies a matrix operation to our input vectors, whatever you're providing, that matrix has a unitary constraint, right? So basically what this does is, this is nothing but a linear regression. This quantum computing circuit is nothing but linear regression without any bias under unitary constraint. So you can call this as unitary linear regression without any bias. Okay, fine. So hope this point is clear. Now we'll move on. What exactly is a matrix vector multiplication in linear algebra? So what exactly matrix vector multiplication does is basically you have this kind of setup. Let's say this is your on 2D dimension, this is your x and this is your y. You have some matrix that you can multiply. So you have a vector here that will have some angle. What this matrix will apply a scalar and rotational transformation on it, right? So it will apply scalar and rotation transformation on whole space on the vector in which the vector is. So basically it will embed the vector, like it will embed the vector in such a way. So let's say you have 2 vectors here, so it will change. So if this is your x, this is your y, initial y, initial x, it will change the angle between the axes as well. So this will be your transformed x axis, this will be your transformed y axis. It can preserve the norm. So a unitary will preserve the norm here, as in it will preserve the 90-degree angle in between. And what basically it will do is transform this vector, right? It will transform this vector. So if it transform one vector, it will transform the remaining vector, right? But this is all happening in linear space. So if you're getting the point, as in whatever of our quantum encoded input vectors are there, quantum encoded input vectors, those will be let's say for MNIST dataset we have taken that as 60,000 numbers. So each class roughly has 6,000 vectors. So all those 6,000 vector, after applying a unitary matrix in this space, will undergo linear transformation. But what actually like a neural network does, or other classification approaches does, is basically applies a nonlinear transformation. As in, the data set for segregation requires nonlinear boundary. So what exactly I mean by that is this, if it is clear, we'll move ahead. So unitary specifically applies a linear transformation onto the all the vectors. Okay, fine. And what it exactly does is separates, as in this 2 dimension. Let's say you have 2 classes which can be represented, which has 2 features which can be represented here. So it will transform the space in such a way that these are all maximally linearly separated. But if the boundary of separation is not linear, as in if the data set, for example, you can find this so example used many times, if the solution is like this, you cannot construct this kind of setting, at least if the dimensionalities are maintained. So this kind of setting, this nonlinear transformation, you can't do. So that is why, like, we are moving on to our our algorithm. So I hope this is clear. So the next point, what exactly is a nonlinear boundary of separation? This is nothing but a nonlinear boundary of separation. For MNIST dataset specifically, the boundary of separation is having the degree 3, as in let's say MNIST dataset only has all the vectors only has 2 features which you can plot. If you can plot this, you can use PCA to visualize this. There are many sources available online, so you can visualize it in 2 dimensions or 3 dimensions just to see the separation boundary. It will be having some polynomial structure, as in this has a degree 3. Okay, so exactly for this is just for MNIST dataset, and MNIST dataset has been around in the 1990s as well. So it started from 1990s. So it's kind of a simple dataset. Why people call it a simple dataset? Because the degree of the dataset is 3, and it can be many models give the accuracy above 90% to it. So the number of parameters or the number of layers in the neural network required to approximate this degree or approximate the function, underlying function of mapping from input to output are very less. So number of parameters required are very less. Okay, so the complexity of this MNIST dataset is very less. But since this has been benchmarked all over, you can find many resources online where it has been benchmarked exactly. Like best accuracies has been reached of around 99 point something. So to achieve this degree, in our algorithm, we follow our approach. So we'll move forward with our approach. Why exactly we have used that kind of setting? There are many other approaches for incorporating nonlinearity. There is QSVT, like one of you can increase the size of the input vectors, that mapping, but that increase, if you look into document, that increase is very fast when you go into that kind of 1024 dimensionalities of that vector, as in the permutations combination of 1024 for degree 3 itself is non reproducible on a classical computer itself if you compute that number of the vector. So that is why you can perform it on a quantum computer if you have that kind of accessibility to the number of qubits and if you have fault tolerant access. But it will be limited to again lower degrees only. So without going to that, we have changed the architecture itself. Moving on, so this you know the basic structure. Then you have your input vectors, you have your quantum circuit, that is unitary quantum circuit, and then you have your output vectors, right? So now we know that MNIST dataset is not linearly separable, right? Means linear separation will give certain kind of accuracy. It will give the probability amplitude. So if you look carefully, if you run the code given to you in amplitude encoding setting, you will find that the vectors after mapping will be in this range, 0.8, 0.9 for the indexing of the start for class 0. Then the remaining vectors for the, let's say, last vectors will be in this setting, like 0.9, 0.8, or sometime it might so happen like this is 0.10. Because this per se cannot be exactly linearly separated, this data point. So this will have a uniform so at first position also this will be having this probability amplitude, at last position also it will be having this probability amplitude. Then so that is why this is causing the error. And if you look at the accuracy that we get, the maximum we can reach is up to 87% for amplitude encoding, that too with the minimax scalar, and 90% for binary encoding. But that binary encoding is reduced. So as in reduced, we have quantized the pixels from 0 to 16 as explained in the first lecture. And we have maintained that dimensionality to be computed on a classical computer that is available to us. So we have maintained that vector encoding to this dimension. So that is why, but actual dimensionality, if it is 255, it might give an accuracy that is better than this. So let's say 92, 93 it can go up to, but still the point remains that it only linearly separates the data. So here you're increasing size of the input vector. So that is why you are having that increase in the accuracy part. So moving on. So this is your structure which you can remember for now, and we'll continue on this. So what exactly, so why the need for our architecture you understood. So what exactly is our architecture? Will begin now. Input vector, mapping, unitary mapping, output vector. Now this is your forward approach, right? As you're going from your input vector mapping to your output vectors, that ideally it should be what? Target vectors. But ideally it should be target vectors, but since the data is not linearly separable, what here will be the unitary at the rate x, as in whatever unit of separation you have here multiplied by all the input vectors. Like this will be let's say this data 60,000 cross 1024 dimensions. This is 1024 cross 1024 unitary matrix, and then this will be your 60,000 comma 1024 vectors, right? So hope this is clear, as in an array. uh, so uh, so it has 60,000 samples, and each sample is nothing but a vector having 1024 features. So but the target vector ideally is not reached. This is your actual vector unitary at the rate x, right? So now like this is one of the forward approach. So why not go from target vector back? So this is one walk you have experienced, right? This unitary evolution is what we call a walk. Whatever quantum circuit operations we have not decomposed into U3 and C0, but this unitary evolution of the all those input vectors. So ideally all the quantum algorithms presently, so cron Joule, if we consider Gross algorithm, Shor's algorithm, it has one-to-one mapping. VQA has one-to-one mapping. But for classification, generative AI approaches based on the conventional classical learnings, it has like multiple data points, as in multiple as in huge data sets, input data sets. So it's not a one-to-one mapping per se. So like to get around this is one of the algorithms we have thought. So why not go from the reverse approach, as in reverse walk? So we have taken this as a target vector, then we are applying a unitary, then this output vectors. So the code will remain the same. So if you look into code, we'll go through the details of the code as well. The ideally this should be your input vectors, and if the data set was exactly linearly separable, this would have been your input vectors. But what happens is you get the vectors, those are not input vectors. So this is nothing but the output of your reverse walk. So this is what we meant by reverse walk. And if you look into the papers, like quantum walk, it's a similar like phenomena. You are having a unitary evolution on the input vector, but that input vector is single in number. So what exactly they mean by quantum random walk is nothing but the probability amplitudes. They are going from zero state to 1 by root 2 using a Hadamard gate 0 plus 1. So they are increasing their probability space having of the probability amplitude of this Ket notation of one state. So that is what they mean by quantum walk. Here we are applying unitary evolution in the forward direction, in the reverse direction. That is what we mean by quantum walk. We are applying unitary evolution only, but this is many to many mapping, not one to one mapping. Okay, fine. So moving on. This is fine. Now this what you got. Let's say this is your actual output one, right? And this is your the forward. This is your forward approach, forward. And this is your reverse actual output one. Okay, now like discarding this, just keeping this and this into the picture. Now this will form as your input vector, this will form as your output vector. So now if this is clear, you have to continue this process. So what exactly this will look like in terms of unitary evolutions? If we look into this, if you represent all the state vectors in your Hilbert spaces using a circle, then all this data sets lie here. We are not segregating the classes per se, but there will be some segregation boundary, linear segregation boundary between the classes. Then you're applying your unitary, you are forming your, so this will be your input, this will be your actual forward output, one. Then from the reverse, let's say this is your target vectors, you have to reach from here to here. That is your objective. So from the target vectors, you are using a reverse unitary. Now like since we are in inspired domain, you can try experimenting this with a non-unitary as well. So you know the code, you just have to remove the constraints of unitary imposed in the loss function of ML. You just have to remove the constraints imposed in the SVD matrix, as in if you look into the matrix, we have removed the eigenvalue matrix of the SVD. So that function you have to keep it at traces, and it will return a non-unitary matrix of transformation. So so you can experiment with that as well, as in the system will be an open system. Target vectors, you will apply a reverse unitary. This will be your reverse actual output 1, right? So now similarly you will do this operations multiple number of times. So what we found actually is the interesting point here to notice. I will come back to this figure, but the interesting point here to notice, okay, there is quite a lot of scribble here, but okay, interesting point here to notice that if you look into the linearity norm, as in the norm difference between this vectors, whatever they are present, and this vectors, it continuously reduces as you move on. So from input vectors to target vectors, or not input vectors to target vectors. So this actual forward vectors to target vectors will have your one norm, right? That norm, if you find the norm of this, so what exactly is the norm is nothing but the Euclidean distance between the vectors, corresponding vectors. So that is what we are trying to minimize here. So that is minimized here. So actual forward output 2 and your, if you look into difference between this and the target vector, it will be minimized further. Or if you take the difference between this and your corresponding actual reverse output also, it will be minimized further. So that is what we found interesting here, because if you look into the conventional, if you just keep this as your first output, that is what a conventional quantum algorithm does. If you just keep this as your first output, then you take the difference between this and this. For a neural network, if you, instead of using a unitary matrix, if you consider a neural network with some parameterization, a random value, not a random value, a near about value is nothing but 5.195. So that is the norm value, average norm value between these two vectors in these two Hilbert spaces. But unitary will have some 13, or in that kind of, not 13, it has 21 point something as the norm distance. You can verify this value per se. You can take just the norm difference between this and this value will be just 5 times of what neural network gives. So that is what we're trying to minimize using this kind of algorithm. So hope you got the clarity. So this approach is nothing but straightforward. This will be a forward walk, you can say, or forward unitary evolution, and this will be a reverse unitary evolution. So and it will meet at certain points. So whatever like number of iterations you want to give here, so the code has some 47 iteration and the code is not optimized. So forgive me for not giving a proper definition there. There should have been just one block for forward approach. There should have been just one block for reverse approach, having the proper definitions given there with proper arguments, and then that function should have been called multiple times for 47 or 48 iterations, but the code is just repeated. So that is a okay, not an efficient code from our end, but try to do that as well. Efficiency of the code you can improve. So this will be having a meeting point, as in the number of iterations you have in the forward approach, the number of iterations you have in the reverse approach will have a meeting point, whatever number of iterations you want to curve it into. Now the point is that whatever unitaries you have, so whatever unitaries you have multiplied it. So this is nothing but your first walk of the unitary. This is nothing but your first forward walk, second forward walk of the unitary. Whatever forward walks you have, that forward walks should map to your middle state, right? Should ideally map to your middle state after multiplying this all, right? Now if you have this, and this will be nearer to what you have in the reverse approach, right? So this state will be nearer if you are having like that kind of number of iterations. Reverse state, and this will be having lesser Frobenius norm. So these two states will be nearer. Now you can apply your unitary dagger operation here, unitary dagger operation from here, and perform a reverse path. Unitary dagger here, then this, the unitary dagger here, unitary dagger here, unitary dagger here, and then you will get your target state. So that is the ideal end. So how many iterations it required from to go from this to your middle state to your output state? That is a point of research. You can try if you are not having that kind of compute. So you can try reducing the size of the vectors just to 64. You can try experiment with the data size as well. You can reduce that as well. The accuracy doesn't affect that much. It's just 2-3% affection accuracy. But what we're trying to do is minimize the distance between the what our actual target vector required is and what we get from here. That is the sole aim of the algorithm. So hope this is clear to both of you guys.
Yes, actually.
Yeah.
So like I have joined from a tab, and my laptop is having a extensive code running on it. So could you please one of you guys do me a favor of opening the code and sharing the screen with us, so like we can explain it from there itself.
Yes, Akshay. One second.
Yeah. And if you want to go through quantum random walks, I suggest going through this paper, or like you can find many resources online. So no need to recommend the paper. Yeah, but this approach, what you'll get is linked to our approach, but our approach is an inspired setting. So what we have like discussed here, that will be like exactly our project, and that will be our exact like implementation of the project. You did not go into this quantum works details here, but you can have go through just as a side read, and you can incorporate like if you get an idea from here into our algorithm as well. So yeah, so what we're trying to do basically here is linearize the data by following this approach, right? We are trying to linearize the data. So like yeah, so what we're basically this middle state, what we are trying to achieve from this middle state, it will be a randomly supervised superposed state. That is what we're trying to achieve. If this will be a randomly superposed state, then we have like succeeded, because from there, if both are randomly superposed states, then like it did not you need not worry which unitary you can apply. So from here itself, if both are randomly supervised, you can take any states, you can apply your unitary daggers, and then you can get your target state. So that is the aim. And then you'll discard all this, you'll just follow the forward approach, and you'll just keep the unitaries, the subsequent unitaries. You did not keep the vectors in between. So once this is done for the training data set, you have to do the same for the test data set and then get the results. So for how will the inference work? You will have these unitaries all like as a parameters, you will have these u daggers all as a parameters, and then you'll reach the target states, and whatever target state, based on that you can classify. That is the aim. Yeah, yeah, that's the main point. I once more I'll try to like go through. So this is the point, like yeah, just so yeah. So uh, yeah, thank you. Yeah, so where was I? Yeah, so the state, as in the forward approach, last state, as in how many number of iterations you will do after applying that unitary. The last state should be near to your superposed state, as in randomly superposed state. What you will get after applying a Hadamard operation, or what you will get after just 1/1 root of 2 raised to n, and all the in between values are 1 1 1 1 1, like that. It can be -1 as well, not an issue, because after squaring that, the addition should be 1. That's the whole n. So not an issue. It can be any value, but this should be the case. Okay, 1/√2. This is your state which you want to achieve from the forward approach, and this is the state which you want to like achieve using the reverse approach as well. Because once you achieve this, then only a reverse approach is possible. As in, if you apply your unitary dagger on this, then like you can get your target, you can get to your target vectors. So like just to continue forward the discussion, like if a loss of information is needed to achieve this state, if certain loss of information is needed to achieve this state, so ideally we should achieve the state. But if you did not achieve the state, then what conclusion we can reach is some loss of information from your input vectors is needed to achieve this kind of setting. So that loss of information you can try incorporating a non-unitary. That also approach you can try. So that can be achieved. So it can form as an open system, and there will be a loss of information. If that too, like it's not giving the ideal result, then what you can try is incorporating no, but yeah, we'll limit to this setting. Can you please share your screen?
Is that visible, Akshay?
Yeah. Okay, so like the number of days the task has been given. Okay, so kindly go through the task written there. Like it has been like 2-3 weeks. I don't remember what exactly are the tasks written, but kindly go through based on the explanations given here. Like we'll just go ahead with the code. So in the first code block, which you already know from our first session, like this directory you have to first change, so you already changed that, and then what this data set basically does is convert it into numpy array. Like what this code block essentially does is convert it into numpy array, separates the images and the labels as done in the second definition, and then it separates as per the like digits, and then yeah, so here we are resizing, reshaping our 28 cross 28 MNIST data set to which are gray pixels, which two are desired like pixel size. So this is the new size. What you are deciding is 32,32. That is what is like done in the code. Then this is nothing but the resized digit images we are yeah, so we have plotted that as a proof. You can show after running the algorithm. Then this digit 0, digit 1 are nothing but you're converting that, you're appending that to all the image arrays to a list, and then you're flattening it and normalizing it. That's the whole purpose of this. So that is done here as well. This dot reshape n square comma 1 and np dot linear norm. This operation is nothing but normalizing that. So after that, like yeah, so now limiting to the data set, what you can do is change the number of pixels from 32,32 lesser value to save your compute time, and also this data set size also can be reduced from 5,000 per label to let's say 500 per label. Yeah, so moving on, like this are nothing but our plots, and yeah, so yeah, so these are the plots after reshaping the second plot. Now we have also discussed the complex encoding part, right? So this C float is specifically for that. You can try removing the C float, just keeping the np dot float, and depending on your compute power, you can make it 64, make it 32. I recommend 32 is a better option here because you did not use the unitary internet transfer the unitary, so no any. So second code block, so we are at second code block. Yeah, this is code block input state vectors. Yeah. So this reshaping operation, it's just reshape to the our conventional shape after converting into the array, after appending all the input state vectors to the list. So this is our main code, the second the third block. So layer one, what is basically does, we have defined our target states, which is again a point of research for you guys. So this is a equal spacing target states which we have come up with, as in this acts as an equivalent to one hot label encoding in your neural network architecture. And there are like many possibilities which you can explore here, and this is nothing but your first method of applying. So this compute orthonormal matrix, what it basically does, we already like discussed that in detail in our first session as well. So this orthonormal, this nothing but SVD decomposition, and then you are removing the eigenvalue matrix and just multiplying your eigenvector matrix to get that unitary matrix. So what changes you can do here is, instead of returning orthonormal matrix, you can return M as it's written in the code as well. So, and then orthonormality is verified, like what extent the orthonormality is present. So if you increase the data type to let's say float 64, then you'll get the number, the row orthonormal, column orthonormal to be in the range 1 minus 10. So 1 e to the minus 10. So that for increasing the accuracy, you can increase it to 464 as well. Now this is nothing but the multiplication, as we discussed, matrix vector multiplication. So this layer one unitary is nothing but whatever output vector unitary you got multiplied by the input vectors for all, for I in the, so enumerate. So this is nothing but I index, and then M is the vector in that. So, and then if you look into this error one, print error one, if you're doing like first error, what you will get is this layer one unitary is nothing but the output, right? So what we discussed, our actual output, this is your actual output minus the target states combined what you have. So this is very large value, and neural network has a value of 5 point, right? So again, coming to the neural network, so what exactly happens in the neural network is, specifically there are neurons which activates and deactivates. So as per that phenomena, like you will have to take 10 separate unitaries, but that's called for a different project. but just to give you a rough understanding, you have to take in 10 separate unitaries because you don't have a conventional on-ing and offing of a neuron here, right? So that is why a separate like for a separate class a separate unitary needs to be done. But since algorithm is totally different from that, we are like moving in forward and reverse approaches to get to our target states. So this is kind of a diffusion approach. So basically you are like following in the forward approach. What you're doing is trying to noisy like make the image noisy, as in all the input vectors you're trying to go to superpose, like should reach after like for forward walking should reach that superpose state. That superpose state is nothing but your noise. That will be a purely random noise. So that random noise from the reverse operation, you're trying to like go back to your original state, or like your target state. So that is the diffusion. So we are following kind of a diffusion approach. So if you're like aware about stable diffusion approaches, so this is a similar approach to that. And by the name forward and reverse walks, it has been already clarified. So hope this first code is clear. Then this is done similarly for the test data. Similar operations are done here, to keep the operations coherent, and whatever unitary we have, the input vectors are done. Like you can say matrix multiplied, that unitary matrix multiplied, and this is nothing but a linearly regressed output vectors uh, for test. But here, yeah, a test is necessary once your train vectors work. So if you look at the end of the code, there is no code written for your test vectors. You have to write it on your own for getting that inference. But like just to explain the concept, we'll move on the code. So hope this is clear. Yeah. Okay. Now this is your code block. So what this basically does is this so this is nothing but your, once you have the layer 1 forward approach, so here the layer 1 name is given. What we are trying to give a name was like actual forward and actual reverse. So this is nothing but layer 1 unitary reverse, layer 1 unitary forward. So previously forward is done, this is nothing but reverse. So same code. So what you can try doing is just write a definition. In that definition, like for forward approach one definition, for reverse approach one definition, mention the arguments of input states, output states, and that unitary matrix that is what you'll return from the code. And then two just code blocks you will write, and then call the same functions again and again for your 47 48 layers, how many times you want to like iterate through. So that you can do instead of, so same code block is repeated again. So this print function, if you look into it, is minimizing. So layer 2 unitary minus target states one combined from okay, so this is not minimizing. Why it's not minimizing? Because this is a reverse approach, right? That is forward approach, this is reverse approach. So 138 and 146, if you look into the second application of this, as in second iteration of forward and second iteration of reverse, it will be lesser than 138, it will be lesser than 146. Yeah, please move on with the code. Yeah, this code is all the same. The last, yeah, after this as well. Yeah, the error, if you look into this error, just go yeah, this error if you look into, this is reduced, right? 43.90947, this error is reduced. So this is what we are trying to achieve. And the error, if you remember, is nothing but 5.195. So that error by a neural network. Yeah, so it's a rough figure. For the neural network it has been trained on, if you train it on different neural network having different parameters, the value will fluctuate by plus minus 2, but that will be a rough number. So that is what we're trying to minimize. Hope the code understanding is clear. Same code is like repeated again up till 47 48. So yeah, kindly write the definitions, two code block, give arguments input and output target vector. Same code you have to like take into that definition, return the like matrix, orthogonal matrix or unitary non-unitary matrix, and then call their functions 47 48 times. The number of code blocks are just 3 or 4 for this code. And in the code, what you have to specifically do is how many iterations are needed to go to your target states. Then here we are following like you have to research with unitary non-unitary. Here we are following SVD approach. You have to research with QR approach, you have to research with ML approach. And then like you can go through other documents as well and come up with a novel changes in the architecture that we can create, or some loss of information in the architecture that we can create to get that superposed states in minimum number of iterations. That is your research. So hope this is clear. And like you have to tabularize all the findings you have to make. So error, whatever rates you are getting, right, that error also you can tabularize. So what interesting thing is found here is that the error fluctuates, as in if the error in the first column In the forward approach, if it is some 67, then that same error will propagate to the second column, if you look into, and the vectors also will be moving back and forth. So that is an interesting point to note. Even if I explain, it will not be clear to you. Once you look through what are printing after printing the output vectors, forward vectors and the reverse vectors, you will get a clear cut picture. So yeah. And kindly go through the tasks written there. Like I have thought carefully about the code and the tasks are written there. We have thought carefully about code and the tasks are written there. So like as of now, it's been 2 weeks after giving the task. So I'm not having, I have not gone through the code per se, but you can have a detail. And if you have any queries or like any like new findings you want to discuss, you can ping us. Yeah. So if we go into the last, just to give a interesting like findings here, you go into the last 40 till whatever the code is run, 47th or 40th layer. Yeah, so see there is load and save, right? That is done. So why that was done? Because like my laptop after 21st or 22nd iteration was giving a memory computer because it can't save all the unitaries in 8 GB RAM itself. So that is why there was one kind of jugaad that we did. So we saved the like input and output vectors for that corresponding layers, and then like we repeated the same code for forward and reverse again, repeated the iterations. Yeah. Yeah, and this is also written, right? These are also your tasks. So continue the forward approach and then finally implement the forward architecture to map the input vectors to the target state. So hope this is clear. Like the main thing or the main objective is the input vectors, the middle iteration or the middle where you stop your forward iteration, where you stop your reverse iteration, that too should be very close to each other, and it should ideally be a superposed state, a randomly superposed state. So, yeah.
Akshay, I have a small query.
Sure.
So basically, for the feature vectors, you were trying to encode it through the amplitude encoding. Am I right?
Yeah. That is also one of your tasks. So, please go ahead with
So,
the question.
so the thing is like, should we also implement it with angular encoding also, or amplitude
Yeah.
encoding is just fine?
Yeah. That is also one of your tasks. Like, I think it's written there in the top block itself. Implement it for other encodings as well. Here also it is written, right? Second line.
And also, while amplitude encoding was done in the code, should we normalize it as well? Like there may be a loss, right?
Okay, so amplitude encoding is nothing but normalization of the feature vectors of a classical data set. So those are nothing but your probability amplitudes. So yeah, those are normalized here.
Like the thing is like, let's say we have a vectorized form for that image like that. So
Yeah.
in that case, when we are trying to normalize it, like before normalizing, we have just added, I mean, like use the amplitude, right?
No. That normalization is the thing, but your amplitude encoding. So yeah, so that normalization line that you added, right? nb.energy. If you go into the top code block, top first code block, that line of dividing by np.lineargy.norm and reshaping it to n square comma 1. So this line, this digit 7, let's say 7 plus dot reshape n square comma 1 dividing by np lineargy norm of digit 7. This is nothing but amplitude encoding. So what exactly is an amplitude encoding? Basically, the pixel positions, you're flattening the classical data set, the pixel position should have a norm for that particular vector to be 1, because that is what the Copenhagen interpretation of quantum mechanics tells us. Whatever unitary evolutions you will apply, it should be preserving the probability norms, and that norm should be 1. Yeah.
Okay, actually, I got it.
So hope this is clear. So you're thinking like amplitude encoding is some form of other encoding.
No, the thing is like I saw a different example where they didn't use a normalized vector, so I just got confused.
So this is nothing but your normalized vector. This
Yeah.
what your code will return, right? So this is nothing but in your for loop. So what it basically does is it will calculate the Euclidean norm, as in it will square root squares of all the scalars at that respective element positions of that vector, of that particular vector, and then divide it to your scalar value. So that is nothing but this operation, what we are doing here.
And
Oh,
also another thing, like when we are doing SVD in this code, like the orthonormal condition wasn't satisfied, right?
yeah, it is satisfied to the scale of 1e to the minus 6. If you look into the code, check orthonormal definition of orthonormality. Can you please go in the second code block? So in the definition of the verify orthonormality load, if you will reduce this yeah, verify orthonormality is written there, right? This torch all close, it will take a value, so it will have in the argument one more function. So what is that function exactly? You can put it in one more argument, how much close you want this to be. Like you can define it to be 1e to the minus 10, 1e to the minus 6. Our code specifically for here is taking float, so the difference is 1e to the minus 6. So if you mention this, if you change the code, or there will be one more argument here, if you mention that there should be 1e to the minus 6 norm, then it will return positive, not an issue. It will return a true, so not an issue. You can change the code from here. What you can do is you can add an if else statement. If you into udagger and np linearity norm of that is greater than or is equal to, or minus I is equal to 0, and minus np dot linearity of norm of I is equal to 0, then that case to what extent, as in less than some value, so np dot linearity dot norm of u into udagger minus I less than 1e to the minus f, it will write, then print that u is unitary, or else like print u is not unitary. That scaling you can define either as an argument here, or you can change the code, and then depending on that, whatever float you're defining, if it is 32, if it is 64, that value will be 1 into the minus 6, 1 into the minus 10. So that range here is lesser, 1 into the minus 10 or something, and what in the code you're defining is float 32. So that is why it is returning a false, not an issue. Still you can verify, right? What you can do for verification, after multiplication of your unitary with your input vectors, the output vector should have the norm still equal to 1. If you print the norms in the for loop, you will print all the norms of whatever vectors you got at the output. It will be 0.99999 or 1.000 to that precision. So yeah, so I hope the point is clear.
Yeah, actually.
Yeah. So any other queries from your end?
Hi, sir.
Yeah. Please go ahead, Prashant.
Yes, sir. Actually, I got cut in halfway only. I will ask from Raven, but I
No
wanted to
issue.
tell you.
This session is recorded. You can go through the session whenever you
Okay,
have your
okay,
convenient time. Yeah, and then you
okay.
can get back to us on Slack. Yeah.
Yeah, oh, sure, sir.
Yeah.
Thank
Okay.
you.
Sure.
I think, are we done, Akshay?
Yeah. We are done, Pritam.
Okay, then we will conclude then. And Ravant and Prasast, if you have any question, please feel free to message us on Slack.
Okay, sir.
So yeah, Ravant and Prashant, like there are like 5-6 point mentioned in the discussion. So kindly take that like discussion to your like into your mind. That is relevant to your project per se. So that 4-5 discussions, that is your research perspective. That should be a research perspective here, and whatever code tasks are mentioned, that should be a research perspective. So yeah. And there isn't any specific document that you can find this. So this is our own finding, and this is our own work. So yeah, this is limited to Heisenberg quantum AI. So please, if you have any questions, you can revert only to us. Like you cannot find this in your document, but you can go through other the concepts if you have any doubts in that.
Sure, sir.
Yeah.
Okay then.
Thanks, Britan.
Okay.
Yeah,
Thank you,
thanks.
Akshay. Thank you, everyone. Bye.
Thanks, everyone. Bye. Yeah.